All right, so today we're doing some midterm review here on campus. So if you are watching this online, hopefully these same questions that are asked today will be questions that you have as well. And of course, you can always email me if you have questions about things that don't get answered today in our midterm review. So what kinds of things did you guys write on your list that you'd like for us to go over today in our review? Balancing equations. I'm just going to list them all out, and then we'll go through samples of each one. All right? So balancing equations. That's a good one. What else? Stoichiometry. Okay. Okay. Yeah. Limiting reagent. Those two go together, so that's good. Okay. Mole conversions. All right. What else? Lewis structures. Okay. Anything else on your list that is not on, that we haven't already put on our list on the board? The quantum model? Okay. Now that's kind of broad, so when we get to that, you have to narrow it down a little bit. Anything else on your list that isn't already represented here? Anything else? All right, I'm going to jot them off to the side so I can erase, because my camera only picks up in a finite region there. So balancing equation, stoichiometry, limiting reagent, mole conversions, Lewis structures, and quantum model. Okay. That way I'm not using up all my board space. Okay, so let's go just straight down our list, because that's actually in a really good order to do things. So let's talk about balancing equations first. All right, make sure I'm staying in the frame here. Balancing equations. So the goal of balancing equations is to get, oops, that's one word, to get the number of each atom equal on both sides. So that's the goal. In other words, if there are 4 carbons on the reactant side, you want 4 carbons to be on the product side. If there are 6 hydrogens on the reactant side, you want 6 hydrogens on the product side. Right? You want to make those 2 sides equal each other. And so what I do, and this is my recommendation until you get really good, but obviously if you have a method that works for you, you can do it that whatever way works for you. I use a reactant product table. That's the way I recommend doing it until you get to the point where you can just do it in your head. Because if you can do it in your head, that's awesome. Go for it. Great. But if you're not to that point yet, a reactant product table is really visual. It's something that you can look at and you can compare left to right really easily. So let's start out with one of the ones that I know is in the lecture packet and in the notes. Let's go through it in person too. Let's do water. So H2, this blank is where we're going to put the number O2, H2O. Now before we get into balancing this is called a coefficient. Okay, that's what these little blanks are. Oops. And this can be any number that we want it to be, right? It could be 1, 2, a zillion, any number you want it to be. Obviously, it can't be 0, right? Because if there are 0 H2s, you just wouldn't write it. You just leave it out. Right? So it's any number up to infinity. And so when we put a coefficient in front of this, that's telling me I've got 1 H2 molecule, or 10 H2 molecules, or 100 H2 molecules, right? So we're going to balance our equation by placing coefficients here. And then we don't want the coefficients necessarily to match. We want the number of each atom, okay? So sometimes students get confused and they think, oh goodness, if I have a coefficient of 2 over here, I've got to have a coefficient of 2 here, right? It's not the coefficients that have to match, it's the numbers of each atom. And that's why I make the reactive product table. So let's make the reactive product table. So once you've got your equation written, I just kind of draw a line. Right? These sides are all products. These sides are all reactants. And then I list everything. And I write them in the same order on both sides. Try not to stand right in front of the camera. Right? I write hydrogen first on this side, so I need to write hydrogen first on this side too, so that when you look straight across, it lines up. Right? Because if you've got H first over here and then O first over here, and you're comparing left to right, you'll get confused. So, how do I know what goes here? There are 2 hydrogens on this side, right? Because the subscript is 2. And the coefficient is 1. 1 times 2 is 2, right? There are 2 oxygens on this side, right? Because their coefficient, if there's no coefficient, the coefficient's 1. Okay, so if there's no coefficient, the current coefficient is 1. 1 times 2 is 2. All right, on the product side, we've got 2 hydrogens. And if there's no subscript, how many oxygens do I have? Just 1, right? So we want the number of each atom. So right now, hydrogen is already balanced, right? 2 and 2. But oxygen isn't. So if I want to turn this 1 into a 2, I can't change the formula, can I? I can't just change this into a 2, because hydrogen peroxide, H2O2, and water, H2O, are not the same thing, right? So I can't change the formula, but what I can do is I can put a coefficient in front of the molecule. So I want this 2, I want this 1 to become a 2. So if I put a 2 right here, now just think about in math. If you've got a 2, right? Oh, I guess that's a bad example. Let's just do that, right? You distribute that inside the parentheses. You're going to do the same thing here. You're going to distribute this 2 to both of these guys. So 2 times 2 is 4, and 2 times 1 is 2. So now oxygen's balanced, but hydrogen is now unbalanced. So how do I balance hydrogen? I have a 2, I want it to become a 4, so I put a what? A 2, right. 2 times 2 is 4. So now we've got 4, 4, hydrogen's balanced, 2, 2, oxygen's balanced. I didn't need to put a coefficient here. If there's no coefficient, the coefficient is assumed to be 1, right? You don't have to put anything there because the coefficient could never be 0. Because if there was a 0 here, you just wouldn't write it, right? So if you want to leave that blank, that assumes that the coefficient is 1. Or if you just really don't like having a blank there, if that just bothers you, and you're like, it's blank, it's empty, you can put a 1 there if that makes you feel better, okay? But that 1 is technically not necessary, okay? So my final balanced equation is 2H2 plus O2 produces 2H2O. Does that make sense? Yes. All right, let's do one that involves a little bit more thinking. Let's do, this is an experiment we'll do in lab. Am I still on the screen? Yes. So we actually do this experiment in lab. This is a reaction we'll do. So let's balance this equation. I'll give you a second to jot it down so that you're not trying to write while I'm talking. And those are all L's, by the way. I try to make my I's look like that so you can tell an I from an uppercase L. I mean a lowercase L. All right. Reactants. products. Again, we want to list everything in the same order so that we can compare nice and neat from left to right. Aluminum, I've got 1 on the reactant side and 1 on the product side. Hydrogen, I've got 1 on the reactant side, 2 on the product side. Chlorine, I've got 1 on the reactant side, 3 on the product side. Okay, so it really doesn't matter where you start, who you choose first. It's entirely up to you. I will advise you, though, if you ever are doing a balancing equation problem and you get stuck and you're just spinning and going in circles, erase everything, start over, and just pick something different. Sometimes picking something different to start with makes life a little bit easier. So, just for fun, let's balance hydrogen first. Because aluminum's already balanced. We just go straight down the list, right? Aluminum's already balanced, so let's just go down the list. Hydrogen's not balanced. So, is 2 a multiple of 1? Yeah, right? How would I turn this 1 into a 2? Right, put a 2 in front of HCl. Distribute it to both. 2 times 1 is 2. 2 times 1 is 2. So now aluminum is balanced, hydrogen's balanced, but chlorine isn't. And now we've got a problem. Because is 3 a multiple of 2? Or is 2 a multiple of 3? No. But I can turn them both into the same number, right? The least common multiple of 2 and 3 is what? 6, right? If I turn this into a 6, and I turn this into a 6, then they'll be balanced. So how do I turn this Cl from a 3 into a 6? 3 times 2, right. So where does the 2 need to go? Right here, in front of the AlCl3. So if I put a 2 here, I've got to distribute it to them both. So that does mess up my aluminum. We'll go back and fix it later. 2 times 1 is 2. 2 times 3 is 6. Let's fix our chlorine. So instead of being a 2 right here, what needs to be right there? Because this is a 1 currently, right? So just put a 6 right there, right? And instead of being a 6, instead of being a 2 there, just turn into a 6. 6, 6. Okay, so chlorine's fixed, but we've messed up aluminum, we've messed up hydrogen, but these are both easy fixes, right? Because aluminum is currently a 1, which means I can turn it into any number I want. So what number needs to go here? 2. And then is 6 a multiple of 2? Yes. So what goes right here? 3. So 2, 2, 6, 6, 6, 6. So everybody, the numbers are the same. So we're done. We're balanced. All right, let's do one where the same element appears in more than one substance. And this is something you'll see a lot, especially in combustion reactions. So let's do ethanol, O2, CO2, H2O. I'll give you a second to write that down. Okay, so here we've got the same substance appearing in more than one compound. So we've got to deal with those kinds of balancing equations a little bit differently. Let's make our table, reactants, products. Okay, we've got carbon. Now look, this molecule contains 2 carbon atoms, right? So I can write that as a 2. How come I can combine those 2 carbons together? because they're in the same molecule, right? If I put a 9 right here, it affects both of these carbons, right? And then on the product side, I just have 1. For hydrogen, I've got 1, 2, 3, 4, 5, 6, right? I can combine all those together. Again, why? Because they're in the same molecule. Right? If I put a 4 here, it affects all of these. And then on the products, oops, I wrote 4 there. Hydrogen. On the product side, I've got 2. Now for oxygen, here's where we got to split it up. I've got oxygen in this molecule, and I've got oxygen here. I need to write this as 1 plus 2. Why? Because if I put a 4 here, it'll affect this one, but will it affect this one at all? No. If I put a 4 right here and I'm trying to distribute it, I only distribute it to this guy right here, and I leave this one alone. Likewise, if I put a 6 right here, right, it would only affect these, but it would not affect this one. Okay, so anytime you've got the same atom appearing in more than one substance, you got to split them up. And then the sum just needs to equal the sum on the other side. So we're going to do the same thing over here. For oxygen, 2 plus 1. So long as the total on the left equals the total on the right, then you're good to go. So let's just go down the line and balance this. Carbon is currently 2 to 1. So how do we balance carbon? What do I need to do to make this 1 turn into a 2? A 2 in front of CO2. Right, distribute it. 2 times 1 is 2, and 2 times 2 is 4. Right? Again, this is why it's important to have them split up. Because when you're distributing, if I had just written this as 3, I'd have no way of actually distributing that, right? It would be a train wreck when I tried to distribute that. Let's balance hydrogen. You always want to start with your easiest ones first. Leave your complicated one for last, okay? Oxygen is definitely my complicated one. We'll deal with it last, although it was currently balanced before I started messing with things. What do I need to do to balance hydrogen? A 3 in front of the H2O, right? And then distribute. 3 times 2 is 6, and 3 times 1 is 3. Okay, so the sum on this side is 7. So I want the sum on this side to also be 7, right? Now I want to leave the ethanol, that's what this molecule is, I want to leave it alone. Why? Why do I not want to start messing with this one? If I start putting coefficients here, it's going to mess up my carbons and hydrogens, which I just fixed, right? So I want to leave it alone. So we're going to ignore that 1 oxygen. So what number, I'm going to change this 2 into a number so that when I add it to 1, I get 7. What number would that be? 6. Can I turn a 2 into a 6? Yes. By what? A 3. 3 times 2 is 6. And now I've got 7. So it doesn't matter how you get to that sum, so long as the sum is the same, right? You can have 5 and 2, or 1 and 6, or 4 and 3. It doesn't matter how you get to that sum, as long as it's the same number. How you get there doesn't matter. As long as it's the same total, you're good. So anytime you've got the same the same atom in more than one molecule, you got to split them up. And then just make sure that their sums equal each other. Does that make sense? Feeling good about that one? Do you want to try one before we go any further? Because the next one I'm going to show you involves fraction. That one's the hardest. So do you want to try one for yourselves and go over it, or do you want to just keep rolling? Feel like we can just keep rolling? Maybe after the next one, I'll give you one to try just to make sure. Let's see. Marker's not really coming off very well, is it? Okay, so here's an example. Let me make sure this one is the one that actually requires fractions. I believe this one may be a fraction. Let's make sure. Let's try this one. Heptane combustion. I think this one will involve a fraction. We'll find out. So carbon, hydrogen, oxygen, carbon, hydrogen, oxygen. We've got 7 and 1. For hydrogen, we've got 16 and 2. And for oxygen, we've got 2 and 2 plus 1. I'll give you a second to write it down. All right, let's just go straight down the line. We'll leave our nasty one for last. How do I balance carbon? Put a 7, right? Distribute it. 7 times 1 is 7. 7 times 2 is 14. And then we've got hydrogen to contend with. What's that going to be? 8. Distribute that. Distribute that. 8 times 2 is 16. 8 times 1 is 8. Right, this one won't involve a fraction. All right, what do we do next?
Balance the other one this side to match 14 plus 8.
Mm-hmm. So what coefficient would that be? 11, right? Because this is 22. So this one doesn't involve a fraction. I wasn't very good at, wasn't thinking about a good example. Let's do another one that hopefully does involve a fraction. Let's see if octane will give us a fraction. Is everyone okay if I erase this one? So it's actually going to be the same products. So if you want to just save yourself here, writing it all out again, I'm going to do a combustion again. I'm just going to do a combustion of a different hydrocarbon. Let's do 2n plus 2, 16, 18. C8H18. So let's do octane instead. So, still in our chart, 8, 1, hydrogen, 18, 2, oxygen, 2, and 2 plus 1. Okay, so let's balance carbon. 8. Distribute that to both. That gives me 8 times 2 is 16. And then for the hydrogen, what do I need to use? 9. Distribute that. 9 times 2 is 18. 9 times 1 is 9. Okay, now we've got a fraction to work with. 16 and 9 is 25, right? Is 25 a multiple of 2? No, it's not. So this is the scenario you run into from time to time, where you've got a number that you're trying to turn a number into, which isn't a multiple of it, right? 25 is not a multiple of 2. There's no whole number that I multiply 2 by and I get 25. So what I say to myself is, okay, first you say, oh, crud, right? Second thing you do is you say to yourself, okay, what number do I need to multiply 2 by in order to get 25? So you're going to do a little bit of algebra, right? You say to yourself 2x equals 25, where x is the number you're going to multiply 2 by in order to get 25. How do I get x by itself? Divide both sides by 2. Right? X is equal to 25 halves. And that's the fraction that I'm going to use. So if I put 25 halves right here, 25 over 2, 25 halves times 2 gives me 25, right? So that does make 25. So according to my chart, I am balanced. However, there's a problem here, because are you ever going to have 25 halves of a molecule? No, it's like saying, do I have 25 halves of a pen? No, that doesn't make sense. You want whole numbers in your final balanced equation. You don't like fractions. So to get rid of that fraction, what we're going to do, clean things up here a little bit. What we're going to do to get rid of the fraction is we multiply everything, the entire equation, by whatever the denominator is. So if the denominator here had been 3, we'd multiply everybody by 3. If the denominator had been 4, we'd multiply everybody by 4. Okay, so we're going to multiply everybody by 2 to get rid of that fraction. So my new coefficient here, 1 times 2 is 2. 25 halves times 2 is just 25. 8 times 2 is 16. And 9 times 2 is 18. And you can go back and redistribute all that through your reactive product table. I don't see any reason to go back through and do that, because all we did is multiply by a scalar factor. But you could go back and redistribute it through your product table, but it isn't necessary. Because if it's correct here, when you multiply the whole thing by 2, it's still going to be correct. Everything's just going to be 2 times bigger. So it won't make a difference. Do we see how we did this one involving a fraction? And that's as hard as it's going to get. So if you can handle that one with the fraction, then it's not going to get any worse than that. That's as nasty as it's going to be. How do we feel about balancing equations? Feeling like we've sufficiently crossed that one off the list? Do you want to try one, or do you want to just keep rolling? Want to give you one to try, or want to keep on going? Moving on to stoichiometry? Okay, let's do it. So you have to have a balanced equation in order to do stoichiometry. But before we can do stoichiometry, I saw mole conversions on our list. So we should probably do mole conversions before we do stoichiometry, because you got to do mole concept before you can do stoichiometry. So let's switch our order here. We're going to do mole conversions first, and then we'll do stoichiometry, because this is a step in stoichiometry. Okay? So let's do mole conversions next. I need some oil cleaner. This is not coming off. At least it's not showing up too bad on the recording. All right, mole conversions. I used to have Avogadro's number on the back wall over there. Now I've just got I had it all expanded out so you could see what 10 to the 23rd looks like with all the zeros, but it fell off while I was gone. So I'll have to climb back there and put it back up. Mole conversions. We've got several kinds of mole conversions we have to worry about. We have to do grams to moles, and we have to do moles to grams, and then we also have to do moles to number of atoms, and number of atoms to moles. All right, so we use different conversion factors for different kinds of problems. That's why we're listing these out. Anytime you're doing grams to moles or moles to grams, you use molar mass. And where does molar mass come from? You get the molar mass off the periodic table. Okay. I'm going to give you one of these little handy-dandy pocket-sized periodic tables. That way, if you're out with your friends and you're having a debate about, the elements, you can pull it out of your pocket and be like, actually, because every self-respecting chemist needs to have a periodic table in their back pocket at all times, right? All right, so anytime you're doing grams to moles or moles to grams, you use molar mass. Anytime you're doing moles to atoms, and this is atoms / number of molecules. Same difference. Here's where you're going to use Avogadro's number. I have students using the wrong conversion factor at the wrong time a lot. So that's why we want to take time to especially state when to use which one. Avogadro's number is 6.022 times 10 to the 23rd. And molar mass, it comes from the periodic table. Right? So know which one to use when. That's the real key to being able to do mole conversions. Because if you understand which conversion factor to use when, you're halfway home. Then the rest of the problem just becomes setting it up, punching it into your calculator correctly. So let's do some calculations involving grams to moles and moles to grams first, using molar mass. All right, so let's see. I'm still in the frame here. Yes. Now I am. How many moles are in? I'm going to delete this up. 25 grams of copper. All right, so you go to the balance over there, you measure out 25 grams. I want to know how many moles that is. So, first thing we need to do is we need to get our periodic table, figure out the molar mass of copper. So the molar mass is that bottom number, right? It's the bottom number on the periodic table, 63.54. Now, different periodic tables will carry out that molar mass, different numbers of sig figs. We're not going to worry about that because our final answer is rounded based on the number of sig figs in the problem, not based off of the number of sig figs on the periodic table. So the molar mass of copper is 63.54 grams per mole. So we're going to set up a conversion factor. We start with the number we're given, 25 grams. Now we're going to set up a conversion factor. We're going from grams to moles. So the unit that you want to go away needs to be on bottom, and the unit that you're converting to needs to be on the top, right? I'm going from grams to moles. So that means grams needs to be on bottom and moles needs to be on top. All right, for copper, because it's molar mass, 1 mole is equal to 63.54 grams, right? We got that from the periodic table. So the number that goes with moles is 1, and the number that goes with grams is 63.54. Does everyone see how we set that up? Yes. All right, now all we do is we multiply straight across and divide up. So 25 times 1 divided by 63.54. So in our calculator, 25 times 1 is 25, divided by 63.54 gives me 0.393452943. Can't tell you the number of students who would write that as their answer on a test and just leave it like that. This is wrong for a lot of reasons. Number one, it doesn't have units, right? You need to always have a unit with your answer. Number two, this number has 1, 2, 3, 4, 5, 6, 7, 8, 9 sig figs. My original number only had 2. You can't have a calculated value that is more accurate than the number you began with, right? So if this number only has 2 significant figures, my final answer can also only have 2 significant figures. Is this 0 right here significant? No, it's just a placeholder, right? So when I round this to my final answer, what will my final answer be? 0.39, right? 2 sig figs, 2 sig figs. And then my units, grams canceled, right? Because if you've got grams in the numerator and grams in the denominator, it cancels. So my unit is just moles. So that is my final answer. Does everyone see how we did that one? Do we need to do one going the other way, moles to grams? It will look exactly the same except the conversion factor would be upside down. Do you want to see one like that, or are you good? And I'm happy to do it. It won't take very long. Do I do it just for good measure? Yes, no, maybe. No? Okay. Do you want to do one with Avogadro's number then, just to see that? Okay. Those are the ones that tend to trip people up more. Number one, because you got to enter an exponent in your calculator. And number two, I see those conversion factors get put in upside down a lot. So we're going to do an example of each, just to make sure we're good at it. Let's do one. Make sure I'm still in the frame here. Let's do number of atoms to moles. And we're also going to do, I'm still in the frame, moles to number of atoms. We're going to do both, just so you can see both conversion factors. So let's do an example. How many moles are in 2.96 times 10 to the 24th atoms of helium? Focus, please. Okay, so we are going from number of atoms to moles. We need to use Avogadro's number. So we take the number that we were given and start with it, 2.96 times 10 to the 24th. This is just an abbreviated way to write that. Oops, I'm out of the frame. Just a smidge. 2.96 times 10 to the 24th. There we go, in the frame now. So this capital E just takes the place of the times 10 to the, okay? Because when you enter this into your calculator, you use a button that looks like this to enter it in your calculator. So 2.96 times 10 to the 24th atoms. Okay, what unit do we want to go away? Number of atoms or moles? Atoms, right? Number of atoms needs to go on bottom. So atoms is on bottom, and moles is on top. Now, Avogadro's number tells us 1 mole is equal to 6.022 times 10 to the 23rd atoms, particles, jelly beans, whatever. And it's atoms in this case. So what number goes on bottom? Avogadro's number, right? Because that's the number that goes with atoms. And what number goes with moles? It's 1. Does everyone see how we set this conversion factor up? So when we multiply straight across and divide up, if you've got your calculator with you, go ahead and pull that out because I want to show you a handy little trick on your calculator. Now, it'll depend on what kind of calculator you have, what brand. On my calculator, which is Texas Instruments, I have a button that looks like this. On some calculators, it's just 1 E. On some calculators, it's a double E. So if I'm entering this exponent, 2.96, and then I hit this EE button, and then I hit the exponent, 24, that tells my calculator I'm entering 2.96 times 10 to the 24th. So if you've got that button on your calculator, take advantage of it. Are you able to find it? And now, times 1, well, who cares, that's still the same number, divided by 6.022 E 23rd. So there's my final answer. 4.915310528. Obviously, that's total garbage in terms of sig figs, right? Because Avogadro's number is a constant, so we don't use it for sig figs. We base our sig figs off of the number of sig figs in the original problem. The original problem had how many sig figs? 3, right? So my final answer needs to have 3 sig figs as well, right? So I round that to 3 sig figs, that would be what? 4.92, right? And my unit is moles. And there's my final answer. So that's going from number of atoms to moles. Does everyone see how we did that one? Now let's go the other direction. Let's go from moles to number of atoms. And if you miss anything or if you want to watch it again, this video will be up today. And I'll put a link to it on the class homepage, like on the very beginning homepage when you log in. So you don't have to dig through YouTube to find it. I'll put a link right there on the class homepage. Let's do one of this kind now. If you have a 2 mole sample of Cl2, how many molecules do you have? All right. Have I given you enough time to write it down? Try not to start working until I give you a chance to write down the problem. Okay, so this time we're going from moles to molecules, right? CO2 is a molecule. That's why we're going molecules. So we start with the number that we're given, 2.00 moles. We're going to set up a conversion factor. Can't find a marker that like keep its life long. Remember, 1 mole is equal to 6.022 times 10 to the 23rd molecules. So what goes on bottom and what goes on top? What goes on the bottom? Moles, right? And what goes on top? We're converting to molecules. Okay, so what number goes with moles? 1, right. And what goes with molecules?
6.02.
Avogadro's number, right. 6.022 times 10 to the 23rd. Just remember this. The number that goes with molecules or atoms is always going to be ginormous, right? Avogadro's number is a huge number. You couldn't count that high in your entire lifetime, even if you wanted to. Right? You could start today and you'd never count that high. That's a humongous number. So the number of molecules or number of atoms is always going to be astronomically large, right? Because if you're calculating number of atoms, that's not going to be like 6. It's going to be a huge, huge, huge number. So you should always have a number on top that's gigantic if you're calculating number of molecules or number of atoms. If you're calculating number of moles, it shouldn't be a huge, giant number. So moles cancels, we multiply straight across and divide up. Dividing by 1 isn't going to change my number. So now I just say 2 times 6.022 times 23rd. My calculator is not smart enough to figure out sig figs. It doesn't know anything about sig figs. It's not smart in that regard. Right, that's what my calculator tells me the answer is. But I have to then go back and round it appropriately. How many sig figs are in 2.00? Are these zeros significant? Yes, they are. Zeros to the right of a decimal are significant. Zeros to the left are not significant, right? Because these are actual measured values. They're not just placeholders. So this value has 3 sig figs. So my final answer needs to have how many sig figs? 3. So 1.20. Now I've had students stop right there and forget the exponent, right? 1.20 and 1.20 times 10 to the 24th are very, very different. So don't forget the exponent. That exponent needs to come with it. And then don't forget your units, which would be molecules. There's your final answer. Now there's one more type of problem I want to do involving mole conversions, and then we'll take a little bit of a brain break because I know we've been at it for a while now. And that is the problem you run into when you're going from, let me just erase everything, molecules to grams. Because that is a 2-step problem. You cannot do that in 1 step. So let's do one like that real quick. Then I'll pause the recording and we'll take a little bit of a brain break. So let's do this one. A balloon holds 9.512 times 10 to the 24th atoms of helium. What mass in grams is this? So here we have a problem that we haven't dealt with yet, and that is we're going from atoms to grams. Can we do that in 1 calculation? No, there's no calculation that allows us to do that. That doesn't exist. That road is closed. Right? We have to go atoms to moles. So that's step 1. And then moles to grams. That's step 2. Okay, we've got to do this as 2 calculations. Because we can't go straight from atoms to grams or grams to atoms. That doesn't happen. So convert atoms to moles, we'll use Avogadro's number. And then moles to grams, we'll use molar mass. So we've got to do 2 problems here. So let's do step 1 first. 9.512 times 10 to the 24th atoms. We're going to convert atoms to moles. So atoms goes on top or on bottom? On the bottom, right? And moles goes on top. 1 mole contains Avogadro's number of atoms, 6.022 times 10 to the 23rd. So I take my calculator. Now we're not going to round until the very end. Okay, we're not going to do our rounding until the very end because this is a 2-step problem. So we're going to carry extra sig figs and then round at the end. So 9.512 times 10 to the 24th divided by 6.022 times 10 to the 23rd. So that gives me 15.795 moles. We're carrying out extra sig figs, right? My final answer needs to contain 4 sig figs. So always carry out at least 1 extra sig fig when you're doing an intermediate step because you don't want to round twice. You only want to round once. So there's step 1. Now let's take this number and use it to start step 2. It's still a good frame here? Yes. Okay. 15.795 moles. Now we're converting moles to grams. So what goes on the bottom? Moles. And grams goes on top. And how do I get this number? Where's the grams number come from? Periodic table, what's the molar mass of helium? 4.0026. And this number for moles is just 1. Right, so moles cancels. So I just take this number times 4.0026. My calculator gives me an answer, 63.2227573, which obviously I can't keep all those decimal places because I would be violating my sig fig rules significantly. Right, so I can keep 4 sig figs, so I need to keep 4 sig figs here. So what is my final answer? 63.22, right, and my unit would be grams. You can always do kind of a self-check. If you're calculating mass in grams and you come up with something times 10 to the 50th, you probably made a conversion factor error, and it probably is right here. You probably had this upside down. Right? If you're coming up with an answer times 10 to the 40th, times 10 to the 50th number of grams, that's like the mass of this building, right? You're not going to have that. So always go back and double check this step. That's usually where you'll make your mistake. All right, I'm going to pause the recording here for a few minutes. We're going to take a mental break. All right, so we finished mole conversions. Now let's do stoichiometry and limiting reagent. We can do those two together. So stoichiometry is broken up into 3 steps. There are 3 steps to worry about when you're doing stoichiometry. Step 1 is you're going to take your starting material, whatever it is, and you're going to convert grams to moles using molar mass. See, this is why we had to review mole conversions first. Then step 2, you're going to take that number and go straight into step 2. You're going to do a mole ratio step. And this is from the balanced equation. This is why you have to have a balanced equation before you can do any stoichiometry. And then in step 3, you're going to take your answer that you get in step 2 and just carry it straight down. So this answer goes straight down to here. This answer goes straight down to here. You're going to turn moles of finishing material moles to grams calculation. So stoichiometry is really just a set of mole to gram problems, just back to back to back. And so long as you follow this order, you're always going to get them right. Just for fun, I want to see if the contrast, I'm getting kind of glare on the board. See if that makes the recording better or worse. Looks about the same. See if that does something for me. That makes it worse. Let's try this for a minute. That might be a little bit better. Can you guys still see okay, right? So, let's go through some problems. All right, here's your problem. Rust is iron 3 oxide. It's formed from is that showing up okay? If you have a that's an E. here's the problem. No, I think I need to turn the light back on. Rust is the common name for iron 3 oxide, and rust is formed from this reaction. If you have a 10-gram piece of rust and you just leave it sitting outside for 6 months, however long, how much rust can form? How much rust can you get? I'll give you a second to jot that down. We've got to do a lot of things in this problem, right? Stoichiometry involves 3 steps. Actually involves 4 because you have to have a balanced equation. If your equation isn't balanced, stoichiometry is going to be a mess. So first thing we need to do is we need to ask ourselves, is the equation balanced? Just for fun, let's write a pink. It's not going to show up at all. Hey, look at that. That pink is getting. Okay, let's do our balancing equation part because it's not balanced, right? I mean, you can tell just by looking at that, it's not balanced. So 1 iron, 2 oxygens, 2 irons, 3 oxygens. Right? This is definitely not balanced. So let's balance iron. That's easy. Just put a 2 right here because that's a coefficient of 1. You can turn it into whatever number you want. How do I turn a 2 into a 3? I can't. So what do I need to do to balance the oxygens? Turn them both into 6. So what number goes in front of rust? 2. Distribute that. So that becomes 4. That becomes 6. What number goes right here in front of O2? 3. 3 times 2 is 6. And instead of having a 2 right here, what do I need to have? A 4, right? So always check to make sure your equation is balanced before you do any stoichiometry. Because if your equation isn't balanced, your stoichiometry is going to be messed up. Okay, that's like step 0. Check your equation, make sure it's balanced. Is everyone good on how I balance this equation? Did I go through that too quickly? So we have a 10-gram piece of iron. So I'm just going to erase this part of the problem real quick. So I always write that information underneath the equation. This is 10. Ooh, that's a nice one. Oh, it's not destroyed by my kids yet. 10 grams, and I want to know how much rust can I make? Okay, so always write what you know and what you're looking for. The problem tells me I've got 10 grams, and that decimal place is significant. It means something to me. Why is that decimal important? That's 2 sig figs, right? If there's no decimal there, would that 0 be significant? But because there's a decimal there, that number has 2 significant figures. That's important. And I want to figure out how much rust I can make. So step 1 of stoichiometry is take your starting material and convert grams to moles. Grams to moles for iron. Okay, so I need my periodic table, right? I'm not going to use Avogadro's number here because the problem isn't asking about atoms or molecules, it's asking about grams and moles. So 10 grams, what's the molar mass of iron? Yes, 55.845. I believe, right? 847. I think, yeah. Okay. And then 1 mole. Now again, we're not going to round until the very end. Because if we round at step 1 and then round again at step 2 and then round again at step 3, our answer is going to be off. So we want to round at the very, very end. So carry out extra digits at step 1 and then carry out extra digits again at step 2 and then carry out extra digits again at step 3. So, calculator time. 10 divided by 55.847 gives me 0.17 Now my final answer needs to have 2 sig figs, so I'm going to carry out 4 just for good measure. 1.1791 moles. Is everyone good on step 1? We agree? All right, step 2 is the mole ratio. And that comes from the balanced equation. This is the only time that you use the balanced equation. Okay? You don't use the balanced equation any other time but step 2. So the mole ratio is what gets you from here to here. So we take our number and we just rewrite it. 0.1791 moles Fe. All right, now it's time for the mole ratio step. For every 4 moles of iron that I use, I produce 2 moles of rust. Does everyone see how we did that? That just comes straight from the balanced equation. For every 4 moles that I use, I produce 2 moles of rust. Why does iron go on the bottom and not the top? That's the one we're trying to get rid of, right? So moles of iron goes away. So we're going to take this number times 2 divided by 4. 2 over 4 is 1/2, right? So you could also say this number times 0.5, either way. This number times 2 divided by 4, or this number times 0.5, whichever floats your boat. So times 2 divided by 4, or just multiply it by 0.5, either way. You'll get, again, carrying out extra decimal places. My final answer is going to need 2 sig figs, so I always carry out at least 3, because my final answer, we don't want to accumulate a rounding error. So my calculator spits out 0.0895, blah, 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 blah. So I'm going to carry out 4 sig figs. 0.89530. And now my unit is moles Fe2O3. Is everyone good on step 2? And now step 3 asks, okay, but I don't want moles of rust because I don't have a molometer. I can't measure out a mole or something. But I can measure out grams, right? I could scrape all that rust and put it on my balance and know how many grams that is. So now I'm going to take this answer and convert it back to grams. So that's step 3. 0.089530 moles Fe2O3. So what we're doing here is we're doing moles to grams. I'm still on the screen. 1 mole. Now what's the molar mass of Fe2O3? How do I get that? We have to do a side calculation. All right, how'd you get that?
I found the molar mass of iron times by 2 and the molar mass of oxygen times by 3.
Great. 55.847 plus 3 times 15.999. And what'd you come up with?
143.688.
Okay. Let's see if I agree. I got something slightly different. What did anyone else do it? What'd you get?
Yeah.
That's what I came up with too.
What is it?
159.691. Did you get that?
I was off. I might have times iron by 3 and oxygen by 2.
Oh, good. But your process was right. Yes. 159.691. Yeah, I got the same number again. So I think you might have just inverted your numbers here. But your procedure was right. By the way, if you're doing a stoichiometry problem and the only thing you get wrong is making a silly mistake here, and you show me your work, I'll only take off like half a point, as long as I can see your work. Because I'm more interested in your process, right? If your process is correct and you just make a silly little mistake here, I know, okay, you know what you're doing. You just made a little math error here. That's only like half a point lost. All right, 159.691 grams. So moles cancels, we're left with grams. So 0.08953 times 159.691. The calculator tells me 14.2971, da, 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 da. I can only keep two significant figures, all right? So that is just 14, and my unit is grams. Is 14 grams a reasonable answer if I begin with 10 grams? Yes. If you come up with 140,000, is that a reasonable answer? No. Okay, so always ask yourself if your answer makes sense, because your answer should make sense relative to the amount you begin with. Does that make sense? Yes. Now, I do want to show you a second way to do stoichiometry. It's not a change in procedure per se. It's just a different way of writing it. Once you feel really good at doing stoichiometry as 3 separate steps, you may have even learned it this way in high school. If you can do stoichiometry as 3 separate steps, and you're like, okay, I'm tired of writing all this stuff out. It's just becoming too much writing. I'm going to show you a condensed way to do it, okay, but only do it this way once you're really good at it. So I'm going to do this exact same problem again. We already know the answer is 14, so all I'm doing is just showing you how to set it up. So you can do it all in one big, long calculation, and you don't have to do all the writing. Now, again, I put a big qualifier on this, which is only do it this way when you feel really, really good about it, okay? Because if you're kind of shaky about doing it as 3 steps, you definitely don't need to be trying to do it as 1 step until you're really, really good at it at 3 steps. So here's what it looked like if you do it all at once. You'd say 10 grams Fe times 55.847 grams Fe for 1 mole. Okay, so that's step 1 right there. All right, grams cancels, now we're in moles. Now we're going to do the mole ratio times 4 moles iron for every 2 moles of rust. All right, so there's step 2. And so moles of iron cancels, we're left with moles of rust times 159.691 grams for 1 mole. So we would say, we'd put it in our calculator, 10 times 2 times 159.691 divided by 55.847 times 4. And when you punch all that into your calculator and round it to 2 sig figs, you'll get the same answer. Okay? So there's step 3. But again, I only recommend doing it as one big long problem once you feel good doing it as 3 separate problems. Okay? If you get to the point where you're like, okay, I'm done this enough times now, I'm tired of writing every single step out, you can go this way, but don't jump to this way until you're good at doing it as 3 separate steps. Because otherwise, you'll start messing up your conversion factors and it'll get messy and make a lot of silly mistakes. How do we feel about that stoichiometry problem? It's just 3 individual steps. Now, limiting reagent is just taking stoichiometry 1 step further. So we're going to keep using the same exact problem. Save ourselves all the writing. We already know the molar masses too. So let's just write this off to the side. 59.69, because I'm going to need space. Okay. Let's just modify this same problem. If you begin with 4.5 grams Fe and 5.5 grams O2, how much rust forms? So in the previous problem, we just left it sitting outside, right? That's an unlimited amount of O2, right? I mean, yes, there's a limit of O2 in the atmosphere, but you're not going to consume all the atmosphere's O2 making that small amount of rust, so we don't have to worry about that. So when we did the first problem, we had an unlimited amount of O2. We just left it sitting outside, came back 2 years later, right? Unlimited amount. But now we're doing this in a sealed reaction chamber. We've got 4.5 grams here and 5.5 grams here. Now we've got a finite amount of oxygen. Okay, we don't have an unlimited amount like we did in the first problem. So this is what happens in the limiting reagent scenario. You've got to do the stoichiometry set of problems twice. You got to do the stoichiometry going from here to here, and then you got to do the stoichiometry going from here to here. So you know what? We already know the answer when it's 10, so let's just save ourselves the work. Let's change that back to 10. So we don't have to do all the calculations again, because we've already done the first step, right? So really all we have to do is do it again for the O2. Does everyone see the difference between stoichiometry versus limiting reagent? Let's just write it out just to make sure. Regular old stoichiometry versus limiting reagent. Use when you know mass of one substance versus limiting reagent. Use when you know mass of more than one substance. The procedure is the same. Okay, you're still going to do stoichiometry. It's just you pick this, you do it multiple times, and then your final answer. Pick the smallest number as your final answer. All right, so when we did it with 10 grams, so 10 grams Fe produced 14 grams of Fe2O3. We did that in the previous problem. We've already done that. That was step 1. So now we just got to go back and do the stoichiometry again using this 5.5 as our starting amount. And then compare our two answers. Whichever number's smaller, that's the answer we pick as our final answer. Does everyone see the difference between regular old stoichiometry versus limiting reagent? Okay. So now it was 5.5. So now let's go back and do it again. Step 1, grams to moles for O2. 5.5 grams O2. Molar mass of O2, right? Each oxygen is 16, 15.9999. So 16 and 16 is 32. We're just going to round that. You could make it 31.999999 if you'd like. But it's not going to change your answer drastically by being off by that 0.00001. Right, so grams cancels. Now I'm in moles. So 5.5 divided by 32 gives me 0.1719 moles O2. Now we're going to do the mole ratio. So take that answer, rewrite it. 0.1719 moles O2. For every 3 moles of O2 that I use, I produce 2 moles of rust. So I take my answer, multiply it by 2, divide by 3, times 2, divided by 3. Again, we're carrying out extra decimal places because we're going to round at the end. 0.1146 moles Fe2O3. And then And step 3 is the moles back to grams. So take that answer and rewrite it. 0.1146 moles Fe2O3. 1 mole of rust. We already calculated the molar mass in our previous problem. 159.691 grams. So times 159.691. 18.2979. I can only keep 2 sig figs, so that's 18. So now we compare. 10 grams produced 14, 5.5 grams produced 18. So my final answer, is it 14 or is it 18? 14, right. So final answer, 14 grams. Pick the smaller number. So if I asked you, what is the limiting reagent? The limiting reagent would be iron, because that's the one that produced the smallest number. And the excess reagent would be oxygen. Okay. So the one that you ran out of first is the limiting reagent. The one that you have leftovers of is the excess reagent. How do we feel about limiting reagent stoichiometry? Pretty good. All right, we're plugging through our list here. We got 2 more things to talk about. Are you okay for me to erase this? You need to go back and see it again. The video will be up today, so you can always go back and look again. Okay, next on our list was Lewis structures, which is completely unrelated to stoichiometry, so it really doesn't have anything to do with what we were just talking about. Okay, so Lewis structure is the shape of a molecule. That's what a molecule looks like. Is there anything in particular about Lewis structures you want to focus on, or just kind of the overall procedure? Just kind of the overall procedure? Okay. So you're going to need your periodic table if you don't have one out already. You can mark this stuff on your teeny tiny little version. I might even have some bigger ones to give you. Up here real quick. I do here. So this is the version that you'll have on a test. It'll look just like this. It'll be blank. There is some basic information that you'll need to commit to memory. So let's just go through that really quickly. You need to know number of valence electrons in order to do Lewis structures. So marker. All right, number of valence electrons comes from the periodic table. So everybody in group 1 has 1 valence electron. So all these guys have 1 valence electron. Everybody in group 2 has 2 valence electrons. We skip the transition metals. That's the group here in the middle. Everybody in group 3 has 3 valence electrons. 4, 5, 6, 7, and 8. Okay, so that's something you'll just have to commit to memory, because the periodic table I give you on the test is just going to look exactly like this. It's just going to be blank. Okay, so you need to know number of valence electrons before you can do any Lewis structure calculations. So, first thing, step 1, calculate number of valence electrons, and that's from the periodic table. All right, step 2, you're going to pick the least electronegative atom and put it in the middle. All right, electronegative atom. Boy, what on earth is she talking about? All right, electronegativity is how well an atom shares electrons. Okay, so think about it like kids. I have a lot of kids. My kids are highly electronegative in terms of their toys, right? They don't want to share. Mine, not yours, mine. So if you're an electronegative element and you're in a bond with an electronegative element, you're not getting your share of electrons, right? They're hogging them all and you're not getting your left out. So if you are an electronegative atom, you don't want to share electrons, which means we should probably not put you in a position where you have to share. Right? My 2-year-old is awful at sharing. So I probably shouldn't put him in a position where he's just going to have to share like crazy, because he'd have a hard time with that, right? So the most electronegative element is fluorine. So mark that on your periodic table. Fluorine is the most electro element. Most electronegative element is the king of not sharing. The closer you are to fluorine, the worse you are at sharing. So electronegativity increases. Going from left to right, electronegativity increases. That means oxygen's more electronegative than nitrogen. That means nitrogen's more electronegative than carbon. Carbon's more electronegative than boron, etc. And then electronegativity decreases down a row. So chlorine is less electronegative than fluorine. Bromine is less electronegative than fluorine. Iodine is less electronegative than bromine, etc., etc. So you want to pick the one who is the best at sharing. Put that one in the middle. The least electronegative atom needs to be the one that you pick to go in the center. Okay. Step 3. Connect all atoms with single bonds to the central atom and keep track of your electrons. I'll show you what that means with some examples. All right, step 4 may not apply if needed, and I put underlines there, only if necessary. Oh wait, I left off a step. Sorry, let me back up. That's step 5. Step 4 is give the outer atoms an octet. First, put extra atoms, extra electrons, excuse me, on the central atom. And then now, if needed, form double, triple bonds. All right, so take a second to jot down the rules, and then we'll go through a couple examples. All right, has everyone got the rules? Let's do some easy examples first. Does anyone remember what the octet rule says? Let's just refresh our memory. Octet rule. All atoms want, wait, that marker's dying. 8 electrons, except hydrogen, beryllium, and boron. Hydrogen only needs 2, beryllium only needs 4, and boron only needs 6. Everybody else needs 8. All right, so let's start with some easy examples. Let's do ammonia, NH3. Okay? So first thing we got to do is calculate number of valence electrons that we're working with. Nitrogen is in group 5, right? It's element number 7. So it's got 5 valence electrons. And there's only 1 nitrogen. Hydrogen has how many valence electrons? 1. And how many hydrogens are in the molecule? 3. So we add those together, it's 8. All right, so our molecule, our final answer needs to have 8 valence electrons represented. Now let's pick the least electronegative atom. Well, this one's a no-brainer because hydrogen can never, ever, 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 ever be a central atom. Ever. Because hydrogen can only form 1 bond. So hydrogen never makes sense to be in the central. So we're forced to put nitrogen in the middle. Because hydrogen can never be in the center atom, they can only form 1 bond. Okay? So nitrogen's in the middle. And then we're going to connect our other 3 hydrogens using single bonds. By the way, if you had drawn this hydrogen down like a T shape, would that be wrong? No, it's the same molecule, just flipped. Okay? Or if you drew it like that or like that, right? It's the same molecule. So each one of these sticks represents 2 electrons. So 2, 4, 6. So I've represented 6. I've got 2 left over. Now hydrogen's an exception to the octet rule, right? Every atom wants 8 valence electrons around it except hydrogen. Hydrogen's content with only having 2. So you don't need to draw these little dots around hydrogen. So I've got 2 left over. Where do they go? On nitrogen. And now check to make sure everybody's got an octet. Well, hydrogen doesn't need an octet, so it's okay. So that one's okay, that one's okay, that one's okay. Nitrogen sees 2, 4, 6, 8. So does it have an octet? Yes. Now let's contrast that to, say, let's do PCl3 just for fun. Let's calculate number of valence electrons. All right, so phosphorus has how many? 5. And there's 1 phosphorus, so that's 5. And chlorine has how many? 7, and there are 3, so that's 21. So my total's 26, right? So who's going to go in the middle here? Phosphorus has to go in the middle, right? Because remember, electronegativity increases going this way. Chlorine's way more electronegative than phosphorus is. Chlorine doesn't want to share, so let's not force it to share. Let's make phosphorus be the one who shares. So phosphorus goes in the middle, so P, and then connect with all single bonds. So just for fun, let's draw this one like this. Just for fun, right? It's not going to make a difference. So 2, 4, 6. I've got 6 represented. I've got 20 more I need to show. So let's give everybody an octet. 2, 4, 6, 8, 10, 12, 14, 16, 18. We gave all our outer atoms an octet. We got 2 left over. Does everyone see why all these guys have dots, but the hydrogens here don't have dots? Hydrogen doesn't need an octet, right? It's content to only have 2. Chlorine is not an exception. It needs an octet. I've got 2 left over. Where do they go? On the central atom, right? So make sure you understand why this one has dots on the outer atoms versus this one doesn't. Because I have students drawing dots around hydrogens all the time. It's like, don't do it, right? Hydrogen's an exception to the octet rule. Everybody's got an octet here. I've used up all my electrons, so I'm done. Now, I know I'm running low on time, so I want to do one example real quick that involves forming double bonds. We've got time just for one more. We'll get to your quantum model question, whoever it was that asked quantum model. We'll get to that at the beginning of class on Friday, if that's okay, because we won't have enough time to get to it. Let's do one real quick example involving a double bond, because I just want to review that one with you real quick. It'll also review an ion at the same time. We'll kill two birds with one stone. Let's do nitrate. What's the formula for nitrate? It's an anion. Right, NO3 minus. Good. So number of valence electrons. Nitrogen has 5. Oxygen's in group 6. It's 3 of them in here. So that's 18. Now we've got a charge to deal with. Okay, when you've got a negative charge, that means that this molecule's gained extra electrons, right? Negative charge means extra electrons. So we got to add one for that. Okay, that's coming from the charge. So always do the opposite. If it's a minus, add electrons. If it's a positive, subtract them out. Okay? So this gives me 24. Who goes in the middle? Look at nitrogen and oxygen. Who's less electronegative? Nitrogen, right? So nitrogen goes in the middle. And then connect my oxygens with single bonds. 0, 0, and 0, 2, 4, 6. Okay. But let's not even worry about that right now. Because we know we have to give everybody an octet too, right? So let's just go ahead and give everybody an octet. And now let's count. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. We've used them all. Just connecting single bonds and giving everybody an octet. Right? Just that act alone gave everybody an octet. I'm out of electrons. So now I go back and check. Does everybody have an octet? Yes, yes, yes. What about the nitrogen? No, it doesn't. So this is where you form double bonds or triple bonds if necessary. What I'm going to do is I'm going to take one of these pairs and I'm going to share it. Dump it here in the middle. Okay? And now nitrogen's got an octet. And because this is a molecule with a charge, we put brackets around it and draw a negative sign. Now, would it be wrong if I put the double bond on this side instead? No. What about if I put it here? That's called resonance. When you've got more than one way to draw a Lewis structure. So if you drew this, that would have been correct. And if you had drawn this, that also would have been correct. That's called resonance. Okay, so that's where we'll stop for today. On Friday, we'll go over any quantum model questions you had that we didn't get to today. We just ran out of time. And I'll see you then.